DePIN rewards only work when networks can prove real service happened. In this topic, we'll look at how physical work becomes digital evidence, checking location, uptime, quality, and fraud resistance before rewards are issued. We've already covered what DePIN is, why incentives matter, and how devices and edge infrastructure are deployed. Now we turn to the key trust question. How does a network prove that real-world work happened before assigning rewards? In DePIN, the hard part is not just paying contributors. It is proving that useful work actually occurred. A hotspot may report coverage, but signals can be noisy. A sensor may submit data, but the device could be moved or modified. Verification turns raw evidence, such as sensor readings, GPS, uptime, and usage data, into decisions about rewards, slashing, and reputation. When that proof is strong, payments stay fair and buyers can trust the network. Proof of physical work is the mechanism that turns a real service into something the protocol can trust. The proof depends on the category. Wireless networks test coverage, storage networks check availability, compute networks verify execution, and mapping or energy networks validate measurements and delivery. Most systems combine device telemetry, cryptographic signatures, network challenges, and outside attestations. The aim is not absolute certainty. It is reliable confidence, so honest contributions are rewarded and fake activity becomes unprofitable. A useful rule is that the proof should match the service being sold. Wireless networks need evidence of coverage, signal, location, and usage. Storage networks care about replication, retrievability, and duration. Compute networks must show that execution happened correctly, often through benchmarks or hardware attestations. Sensor, mapping, and energy networks rely on observations, routes, metered output, or grid activity. The closer the proof is to the service, the harder contribution is to fake. Verification turns a device's claim into a network decision. First, the device or edge node signs telemetry, performance data, or service records. That evidence goes to verification services, which test it against protocol rules and outside data. Oracle or attestation layers then package the result for smart contracts. Finally, the contract updates rewards, reputation, or penalties. The design challenge is balancing accuracy, latency, cost, and decentralization. When rewards depend on physical deployment, location has to be verified, not simply trusted. A device may report GPS coordinates, but that claim can be spoofed or relayed. Stronger systems combine independent evidence: radio signals, nearby Wi-Fi, cell towers, peer observations, and challenge response tests that prove the device is reachable from that area. The goal is enough corroboration to make fraud expensive, while protecting sensitive location data tied to homes, vehicles, or people. Availability is more than a device being switched on. The network needs evidence that it can respond when demand arrives. That evidence can come from heartbeats, ping tests, synthetic requests, or checks by peers. What matters is continuity, performance across hours or days, including latency and missed checks. A node that is merely online may still fail readiness, so reward logic uses history to favor reliable supply and penalize gaps. Verification also has to ask, is the service actually good? For wireless networks, that means signal strength, bandwidth, packet loss, and real user sessions. For compute, it means task success, execution time, hardware capability, and benchmark integrity. For sensors, it means accurate, fresh, calibrated data with low anomaly rates. Quality-based rewards make this explicit. Contributors earn more when the network delivers reliable, useful performance. Challenge response verification turns a claim into a live test. Instead of simply asking whether a participant is online, the verifier sends a specific, often random task. Serve this data, answer this signal, compute this result, or prove you can reach a target. The participant must respond correctly, usually with a signed response, before the time window closes. If the proof validates, reward or reputation can improve. If it is late, missing, or wrong, the service claim remains unproven. A single proof only tells part of the story. Reputation scoring looks across many interactions to ask whether a participant delivers reliable value over time. Uptime, service quality, location confidence, disputes, fraud alerts, and customer feedback can all feed into the score. Strong history can unlock better routing and higher rewards. Weak history may trigger reduced access or extra checks. The design challenge is fairness. Discourage bad behavior without permanently excluding honest new or smaller operators. Fraud resistance starts by assuming rewards will be gamed. If tokens are paid for coverage, storage, sensing, or bandwidth, attackers ask, "What can I fake cheaply?" They may clone devices, spoof GPS, replay signals, run emulators, or form groups that approve each other's claims. A useful threat model separates what the attacker can control: hardware, identity, location, data, and peer relationships. From there, defenses can target the weakest proof, not just punish bad outcomes. Fraud control in DePIN works best as layered defense, not a single gate. Analytics flag signals that look physically or statistically impossible. Peers and independent measurements check whether the claimed service actually happened. Device attestation and signed telemetry make it harder to spoof hardware or invent data. Economics adds another layer. Stake, delayed rewards, and slashing make cheating costly. The goal is simple: reduce trust in any one participant and make fraud expensive, visible, and unprofitable. Verification design is a balancing act. Checking more often raises confidence, but it also uses bandwidth, compute, and battery. Strong identity or location checks reduce fraud, yet they can feel invasive and slow onboarding. Putting every proof on-chain adds transparency, but may be too expensive for frequent physical telemetry. That is why many DePIN networks use hybrids: verify off-chain, then anchor commitments or settlement on-chain. The core idea is simple. DePIN rewards depend on verifiable physical contribution. Networks must prove where work happened, whether infrastructure stayed online, how well it performed, and whether fraud was avoided. Those proof outputs feed the next layers of the system: data, oracles, off-chain infrastructure, security, privacy, and reliability.